Welcome back to the electric circuits topic. Today's lesson is resistance part 2. Your key learning for today is you should be able to recall the equation V equals IR, apply the correct technique for answering calculation questions, analyze a basic practical for measuring current and potential difference in a testing circuit, and hypothesize why we get sparks. Before we get into the new material, let's have a go at some recap questions. Linking back through this topic, answer the following. 1. What is the symbol for current? 2. What is the unit for potential difference? 3. What happens to the current in a circuit if you increase the resistance with a constant potential difference? 4. What is the equation linking current, time and charge? And 5. What do like charges do when they are close together? Pause the video now, have a go at those questions. When you're ready to move on and find out the answers, press play. Let's take a look at those answers then. So, number 1, what is the symbol for current? It's a capital I. What is the unit for potential difference? It's V or volt. What happens to the current in a circuit if you increase the resistance with a constant potential difference? It decreases. The current will decrease if you increase the resistance. Remember those marbles. Number 4. What is the equation linking current, time and charge? This one is Q equals IT. If you've written I equals Q over T or T equals Q over I, that's absolutely fine, but Q equals IT is the typical version of it. Question 5. What do like charges do when they are close together? They repel. So today we have a new equation. What I'd like to do now is just prove to you that actually you know what this equation is going to tell you. You've already done some experiments where the outcome of the equation will actually be very familiar to you. Let me show you. I'm going to introduce you to today's new equation by rearranging it into a format that we've already seen in action, which is I for current is equal to V for potential difference divided by the new symbol R for resistance. Now we've already seen that if we increase the potential difference, we get an increase in current. We saw this in lesson 4. Here's a reminder. So let's turn on the power supply and let's start raising that potential difference. Keep an eye on both the voltmeter and the ammeter at this point. It's going to turn it up bit by bit. And you can see how this ties in with the equation. So increasing the potential difference on the top part of that equation will increase the current if we keep the resistance value the same. Now let's move on to resistance. As we saw in lesson 5, if you increase the resistance, you get a decrease in the current. In order to model this, we use some pins on a corkboard. Here's a brief reminder of what happened. So let's try measuring that current. For this, we're going to need to use a stopwatch. And we are going to count every marble as being equal to 1 coulomb of charge. And we're going to count how many marbles passed beyond this line in the first second. And that'll give us how many coulombs per second past that point. This will give us a value in amps for the low resistance and the high resistance wire. Remember there are 6 marbles on each side. Let's pause it at 1 second. On the left, 5 coulombs have passed that line in 1 second, that's 5 amps. And on the right, 3 coulombs have passed in 1 second, that is 3 amps. So there you could see that if you increase the resistance while keeping the potential difference the same, which was represented by the height of the ramp, then you would get a decrease in current. This is how we present the equation normally. So we have potential difference is equal to V, current is represented by I, and resistance by the new symbol R. V equals IR. This is your new equation for today. So a little bit more detail on that equation then. Potential difference is equal to current multiplied by resistance, or V equals IR. The units for that are volt for potential difference, amp or ampere for current, and a new word here, the ohm for resistance, and it has that capital Greek letter omega. One of my Year 11s last year told me that the way that she remembered how to draw the symbol for the ohm is it kind of looks a little bit like an octopus. I'll let you be the judge of that one. Calculation time! So now it's time to have a go with the new equation, V equals IR. Here is a list of questions that I would like you to have a go at, and here is your checklist to make sure that you cover all the steps that are necessary to get the maximum marks in your examinations. I would like to give you a little bit of an extra tip on this one. You'll notice here that there are some unusual situations. A mobile phone does this, a resistor does that. It's not actually that important what sort of device or what have you they're talking about in order for you to answer these questions. All that you have to do is be able to extract the relevant information. So it will say that there's a resistance of something, or a potential difference of something, or a current of something. Don't be confused by it. For all you're concerned, it could be something along the lines of Boris is electrocuting Hermione's psychotic hamster. You don't have to know any of that. Just take a look for the numbers and you should be fine. Pause the video now. Have a go at these questions. When you're ready to move on and find out the answers, press play. So let's take a look at how you've done. Question 1. What is the potential difference of a radio if the resistance is 150 ohms and the current is 3 milliamps? You should have 0.45 volts. Question 2. The voltage across a 50 ohm resistor is 6 volts. What is the current through the resistor? You should have 0.12 amps. Question 3. The resistance of a mobile phone is 3 kiloohms and the current through it is 4 milliamps. What is the voltage of its power source? You should have 12 volts. Finally, the voltage across a woman when she is struck by lightning is 33 megavolts, and the resistance of a human being is around 1 kiloohm. What current flows through the woman? We are going to assume on this occasion that this woman is actually a human being, and this gives us an answer of 33 kiloamps. If you've written 33,000 amps, that's fine. The question doesn't specifically ask you to answer in kiloamps, but either of those numbers are absolutely fine. If your answers don't match the ones that are in front of you, then make sure that you pay attention to the next few seconds where I will scroll through my workings. Check your workings against mine, see where yours differ, and correct if necessary. So now we're going to take a look at a little experiment where we are going to be measuring the resistance. We'll be measuring the resistance indirectly using measurements for the current and the potential difference. Once you've seen the video, I would like you to answer the following. Number 1. I would like you to draw a circuit diagram for the experiment. Number 2, why did I use a switch in the circuit? Number 3, why did I get a negative reading on the voltmeter and how did I fix it? And your challenge question is to have a go at working out the resistance. What do you think the resistance of the resistor being measured in this circuit is? Watch the video. Afterwards, have a go at these questions. In physics, we often use little devices that give us a fixed amount of resistance. These are called resistors. And they come in all sorts of shapes and sizes. These little ones tend to be used in circuits where you don't need much power. The big ones tend to be used in circuits where you do need a lot of power. So, for example, this one is capable of taking up to 50 watts of power. Whereas these, if you put 50 watts of power through these, they would melt very easily. These two here are also high power resistors. This one's up to 10 watts, this one's up to 50 watts. I've turned their values away from you because you're going to be working out what the resistance is of those two at a later stage. Something important to note is that the size of the resistor doesn't necessarily mean that it's got an influence on how much resistance it has. So, for example, these resistors here, these are 100,000 ohm resistors. These ones here are 1 ohm resistors. They're the same size. Size doesn't necessarily tell you anything about the resistance of the resistor. This one is large because it can take a large amount of power. It's encased in a ceramic so that if it does heat up, it doesn't damage the circuit around it. So, first thing that we're going to do is we're going to start off by giving ourselves a power supply. Also going to need a variable resistor. In addition to that as well, I'm going to put a switch in the circuit, and I'll explain why later. And we're going to add an ammeter so that we can measure the current. And then we are going to add a resistor to our circuit. So now we have a complete inner circuit. Like I said, we do need to measure the potential difference, so we're going to add in a voltmeter. Now we want to measure the potential difference across the resistor, so therefore we will add a voltmeter across either side of the resistor. And that is going to be our testing circuit. Now that we've got that drawn up, let's start adding some components. There's our power supply. Here is where I'm going to put my switch. This is going to be my ammeter. Connect my ammeter to my first resistor that I'm going to test. Let's add the variable resistor. There we should have a complete circuit. Now I'm going to test the circuit before I add the voltmeter to it. Turn on the switch. And now I have a reading for current, so therefore my circuit is complete. Now the reason that I have a switch involved in this particular circuit is because after a while the resistor can get quite hot, especially if you just simply leave the circuit on. And if it gets hot, it starts to not behave as a resistor should. Therefore I'm only going to turn the circuit on when I need to take a reading. Next, we need to add our voltmeter. So here's our voltmeter. This is now our full testing circuit. Let's turn on the power supply again and turn on the switch. Perfect. Notice there that the voltmeter has a negative reading. That means that I have just simply put in the wires the wrong way round. Switch those around and get a positive reading. I would say I did it on purpose, but I didn't. Now turn the switch on and we can start taking readings. Now we are going to use our circuit to estimate what the resistance of the fixed resistor is. Let's look at how the potential difference and the current are related as I adjust the variable resistor. You can pause the video if you wish to do the calculation, but you may not need to. When you think you know the resistance of the resistor, write it down and we will check it afterwards. Welcome back. Now that you've seen the video, I would like you to answer these questions. Pause the video now. When you're ready to move on and find out the answers, press play. So number 1, draw a circuit diagram for the experiment. Your diagram should look something along the lines of this. 2, why did I use a switch in the circuit? Well, it's because the resistor can get hot if it's left on for a long period of time. Number 3, why did I get a negative reading on the voltmeter and how did I fix it? I'd plugged the wires into the voltmeter the wrong way round. To fix it, I just swapped them over. And your challenge question was, what do you think the resistance of the resistor being measured in this circuit is? Because V equals IR, R is equal to V over I. Pausing the video at any point during the experiment, you could see that the value for resistance varied between around 10.2 ohms and 11 ohms using that equation. A good estimate for the value of the resistor would therefore be anywhere around 10 or maybe 11 ohms. Finally, I would like you to think for the final time about your Sparks task. I'll be revealing the answer in a couple of lessons' time, but you've been working on resistance for a while now, so you should have some entries under the words fields, current, potential difference and resistance, and you should be able to draw together a good answer as to why we get sparks using all of those different terms. Thank you very much for watching.